Okay, I think it's already 10 and we should get started. Okay, so you can see my screen, right? Just to be sure. Hello?
Yes, I can see your screen.
Okay, thanks. Yeah, so maybe we can first talk about the exam a little bit. I think you guys did pretty well, I think, overall. So if you consider the full score is 50, right? So the average is 44. So there are quite many of you who are scoring 48 or 49 just because of simple errors. I think one common problem was for the second problem, right? When we talk about we're trying to solve the sulfur dioxide emission rate. So I think quite many of you just stopped at the sulfur emission rate. I think for that, the answer was around 30, 10 per day. But that is not sulfur dioxide emission, right? The sulfur dioxide has a different molecular weight. So basically, this one has a molecular weight of 64. This is 32. So you need to multiply that by the emission rate of sulfur to get sulfur dioxide. Okay, so I think other than that, I don't think there are other common problems. So you're going to need this concept for your team project as well, right? So you should be able to check with each other on what the sulfur dioxide emission rate is. Okay, so this class we're going to talk about the nitrogen oxides control. Okay, so for I would say that for all of these air pollutants, we first talk about their properties, and then we're going to talk about how to control them. So if we do a quick recap of our last class, so last class we mainly introduced the nitrogen oxides properties, right? So we said that the nitrogen oxides are actually made of a group of oxides. So let's say, for example, you could have nitrogen monoxide, nitrogen dioxide, N2O, like N2O5, and so on. But we were saying that among all of these different oxides, basically each of them have their preferred temperature window, right? So for nitrogen monoxide, they are more stable at high temperature, right? For nitrogen dioxide, they're more stable at lower temperature. And it's the same for the other pollutants too, but generally their concentration is much lower compared to the other air pollutants, right? So we said that in terms of the NOx formation sources, right? There's almost half is coming from the vehicles, right? 1/3 is coming from the stationary sources. But in terms of the mechanism, right? For the mechanism of the NOx formation, there's fuel NOx, right? Basically, it's a nitrogen that's bonded to the organics. And when you have oxygen that's burning the fuel, then you're going to convert or release these nitrogen into nitrogen oxides. At the same time, we could have the thermal NOx. Actually, the thermal NOx is a quite important source of NOx. And it is mainly the reaction between nitrogen and oxygen, right? And we said that this reaction is more moving more towards the forward direction at higher temperature, right? And to introduce that, we basically go over the concept of the equilibrium, right? So the chemical equilibrium, what it means is that for any reaction, right? So if it's fixed at a constant temperature, then we can define equilibrium constant, where the final state of all of these reactants and products can be described by that equilibrium constant. Right? For example, for this reaction here, we could define Kp equal to NO to the power 2 divided by N2 and O2, right? I'll further introduce that for this reaction here, if the temperature gets too high, then this Kp also gets higher, right? What that means is that you're going to form more nitrogen monoxide. So another thing that we went over is the reaction kinetics, because we said that the equilibrium is very difficult to reach to. It's going to take a very long time, right? Years or tens of years, thousands of years. But in a co-combustor, there's no way that we could wait for that long. Okay, so that's why we have to derive what is the formation rate of the nitrogen, let's say the nitrogen monoxide, right? And then multiply that by time to find, basically to determine what is the concentration of nitrogen oxides, right? So then let's come to the question. We discussed this a little bit in our last class at the end. So how do we control the NOx formation, right? So here I'm gonna launch a quiz, and then you can spend some time to think about the answer. Okay, so I'll give it 10 more seconds. Okay, so I'm gonna end it here. So the correct answer should be the third one. It's glad to know that this answer is the most selected, right? So if you think about the NOx formation, right? We said that the higher the temperature, the more NOx is going to get formed. This is because of the chemical equilibrium and because of the reactant kinetics, right? So if you calculate the nitrogen monoxide concentration, it should be the reaction rate multiplied by time. So that's why if you increase the time, you're also going to get more NOx, right? So the correct answer should be decreased temperature and decreased residence time, because if you decrease both of them, both from the equilibrium point of view and also reaction kinetics point of view, you're going to have a lower NOx formation, right? So just to test that you guys understand this, I'm gonna launch the quiz again, okay? So, all right. Okay, we'll stop here. So this time we got a full score, all right. Okay, so let's get started with the new information here. As we introduced, right, the temperature and the residence time is going to affect the NOx formation. This is perfectly shown in this figure here, okay? So what this shows is the NOx formation as a function of temperature, okay? So it's trying to control one parameter and see how does the other parameter affect NOx formation. So for example, if we just maintain the residence time at 0.1 second, okay? So let's say in the co-combustor, we always maintain the same time or the same velocity through this high temperature zone, which is 0.1 second. And you can see that the NOx concentration is going to increase exponentially, right? As a function of time, if you just follow this curve here. So the temperature just rise by, let's say 400 Fahrenheit, and you have the NOx formation or the NOx concentration increased by 100 times. Okay, so this is how the residence time affects NOx formation, right? In order to reduce NOx, we need to reduce the residence time. So with the same figure here, if you draw a vertical line, okay, so what this vertical line means is that if you maintain a same or a constant temperature, then these different curves here represent different residence time. You could have 0.01 second, 0.1 second or 1 second. Okay, so you can see that at the same 3600 Fahrenheit, right, the NOx concentration increased from 100 ppm to 6000 ppm. Okay, so just increase the time by 10 times, right? You can get a NOx concentration difference by 60 times, right? So what this means is that basically the residence time is going to affect the NOx formation. So I was probably having a typo here, but initially along this same curve here, it's basically the temperature playing a role, right? The temperature, if you want to reduce NOx formation, you need to reduce the temperature. If you want to reduce NOx formation from the time perspective, right, you need to reduce the residence time. Okay. So the figure on the right shows the internal engines, like the car engines or the diesel engines. Okay, so this is what this is trying to describe is how does the NOx concentration depend on the oxygen concentration. So instead of showing oxygen concentration, what people use, the parameter that people use is called the equivalence ratio. Okay, so equivalence ratio is defined as the air that's required by stoichiometry divided by the actual air amount. Okay, so to just show you how this is calculated, let's say that we're trying to burn methane. Okay, so if you have methane and then you're going to react with oxygen to form carbon dioxide and water. Okay, so if you want to balance this equation, you have 4 hydrogen on the left, so you're going to have 2 water on the right. Okay, and if you further count the oxygen number, right, you need 2 oxygen on the left. Okay, so basically, if you have 1 mole of the methane, right, you're going to need 2 mole of oxygen. Okay, so this is required by stoichiometry. But let's say that we try to burn this methane more completely. Okay, so we provided 4 mole of the oxygen. So according to this equation here, the equivalence ratio is equal to air required by stoichiometry divided by the actual air. That's going to be 2 mole divided by 4 mole, which is 0.5. Okay, so people also use the parameter phi here to represent the equivalence ratio. So basically, if the equivalence ratio is smaller than 1, what that means is that the combustion is in the basically the air rich or the fuel lean condition. Okay, so there's basically fewer fuel for this combustion. And if the equivalence ratio is larger than 1, then you have the fuel rich condition or the air lean. Okay, so let's just use the fuel as the standard. Okay, it's either going to be fuel lean or fuel rich. Okay, so if you look at this curve here again, okay, so this is trying to analyze what is the NOx concentration when you have a equivalence ratio ranging from 0.6 to 1.3. Okay, it's ranging from the fuel lean condition, right? You have more air on the left, and then you have more fuel on the right. So you can see that at the equivalence, at the stoichiometry, where the equivalence ratio is equal to 1, you're going to actually have almost the highest NOx formation. Okay, but if you further notice here, the highest point is actually bent towards the fuel lean condition. So basically, if you have more oxygen that's required by the combustion, you're going to form more NOx. Okay. But if you further increase the oxygen, right, if you add too much oxygen here, the NOx is going to decrease. And this is mainly because of the temperature effect. Basically, you're you're diluting the concentration of the fuel, right? The combustion is going to get more, I would say, it's more diluted, right? The temperature is reduced, and that's why the NOx is going to decrease as we further introduce air, as we further introduce oxygen in here. But what this generally shows is that the NOx formation is going to be the highest when the combustion is conducted at stoichiometry or a little bit fuel lean condition. Okay, so that's why for most of the internal engines, like our car engines, we're going to burn the fuel in this region. Okay, we're going to stay away from the stoichiometry. And that is also the reason why for our car engines, we emit a lot of hydrocarbons. Those are basically the unburned gasoline. And we have to use some catalytic converter to convert these into carbon dioxide and water, right? We don't want these hydrocarbons to be suspended in the air. Okay, so this is for the internal engine. But what is the case for the co-combustion? Okay, so this is the graph that's showing the basically the NOx formation as a function of the equivalence ratio again. Okay, so the equivalence ratio equal to 1, it means that it's a stoichiometry. You can just draw this vertical line here, right? So this is burning lignite or bituminous. So these are different types of the coal particles, and you're burning them at different sizes. So the coal have to be pulverized to get burned, right? So what this y-axis means is the percent conversion to nitrogen oxides. So this is specifically talking about the fuel NOx. Okay, so if you remember, the fuel NOx, we're having an organic component, right, bonded with nitrogen, but actually not all of these nitrogen are converted into NOx. Okay, so they could get formed into nitrogen or NOx. Okay, so nitrogen could be formed mainly because nitrogen is more stable, but NOx is being formed because you're oxidizing it, right? You're providing oxygen into the reaction here. Okay, so now what does this curve mean? You see that basically if you decrease the fuel equivalence ratio, so what that means is that if you increase the oxygen concentration, right? We said that below 1, this is fuel lean. Above 1, this is fuel rich. Okay, so basically, if you go towards 0, it means that you're providing more and more oxygen. So basically what this curve means is that if you increase the oxygen concentration, you're going to get a higher and higher conversion of the fuel NOx into the fuel nitrogen into the NOx. Okay, so for example, if you increase so large amount of the oxygen that the fuel equivalence ratio is 0.1, okay, so if it's 0.1, it means that the conversion of these fuel NOx, 60% of them is getting converted into the nitrogen oxides, while 40% is getting converted into the nitrogen. But if you burn the coal at a equivalence ratio, let's say it's 3, right? You provide 1/3 of the air that's required for the complete combustion of the coal, right? You're just going to get around 5% of the NOx, while 95 are nitrogen. Okay, so basically, right now we have one more parameter. It said that in order to reduce the NOx formation, right, we should do the temperature decrease, we should do the time decrease. But actually, if we decrease the oxygen, we could also reduce NOx formation. All right, so these are the 3 parameters. So here I also have an example problem that we can use to practice this with this curve here. So let's say that we have a fluidized bed combustor, right? This is a co-combustor that burns 1,000 kilogram of per hour of coal with 2% of nitrogen. Okay, so this nitrogen here is in the fuel. And this is at 1600 K, right? If it's 1600 K, we could be using this curve here, right? So it is using an air fuel ratio that is twice of the stoichiometric ratio. So notice here that we're using the air fuel ratio. So basically, if it's twice of the stoichiometric ratio, then the air amount is twice compared to the stoichiometry, right? So what that means is that the equivalence ratio is actually 0.5 because you provide more air, you provide more oxygen into this combustion here. So now we could use figure 16.4, right? Just this curve here, and then try to analyze what is the mass emission rate of the nitrogen oxides? Okay, so it wants us to either express the emission as nitrogen monoxide or express the emission in nitrogen dioxide. So how do we do that? So if we have the coal mass consumption rate, that's 1,000 kilogram per hour. If we know the mass percent, we can first calculate what is the nitrogen that's contained in the coal, right? This is fuel nitrogen. That's going to be 1,000 multiplied by 2%, which is 20 kilogram per hour. Okay, so this is all the nitrogen that's contained in the coal. And then if we know what is the equivalence ratio, right, saying that the air-fuel ratio is twice compared to the stoichiometric ratio, right, we provide more air, and then the equivalence ratio is 0.5, so basically 50%, right? So we could use this curve here, right, and find out what is the conversion rate or the percentage of conversion. This is going to be 35%. Okay, so what this means is that basically for all of these fuel nitrogen here, right? So the NOx, or I would say the nitrogen that can potentially get to NOx is going to be Mn multiplied by 35%, right? So this curve here, this is percent conversion into nitrogen oxides, right? So that's going to be 20 multiplied by 35%, which is 7 kilogram per hour. So right now, we're just talking about the nitrogen, the nitrogen that could potentially lead to NOx formation. So if you want to convert it into the emission of nitrogen monoxide, then that should be this amount divided by the molecular weight of nitrogen and multiply by the molecular weight of nitrogen monoxide, right? So that's going to be 7, and then the nitrogen has a molecular weight of 14, right? Nitrogen monoxide, that's 14 plus 16, right? So this is going to be 15 kilogram per hour. Okay, so this is the emission rate in terms of the nitrogen monoxide. And we could do the same for the nitrogen dioxide. Okay, so basically what you can have is MnO2 equal to Mn2 NOx divided by the molecular weight of nitrogen multiplied by the molecular weight of nitrogen oxide and nitrogen dioxide. That's going to be 7 divided by 14. So 14 plus 32. Okay, that's 36, which is 23 kilogram per hour. Okay, so this is how we can use this curve to find out what is the emission rate of the NOx. This is specifically about the fuel NOx, right? So any questions until now? Okay, so if no, yes.
Yeah, where did you find the 35%?
Yeah, the 35% is here. Okay, so we were saying that we're burning the coal at an equivalence ratio of 0.5, right? Does that make sense, right? We were providing twice of the oxygen, right? Twice of the air. So then you could use this curve here, find 0.5, right? The equivalence ratio, and draw a vertical line.
Oh,
okay. You just want to find what is the value on this curve here.
Okay. Okay. Yeah, I got it. Thank you.
Yeah, this is 35%.
Mm-hmm.
Okay.
Mm-hmm.
Yeah. All right. So now let's get back to the NOx control. Okay. So now, if you summarize the strategies to control the thermal and the fuel NOx, right? We said that for the thermal NOx, we need to reduce temperature, right? What we could also do is to reduce the residence time. And now for the fuel NOx, we need to reduce the oxygen, okay? But for a lot of these conditions, if you just look at it, these are quite counterintuitive, right? We burn coal to generate heat, right? And we don't want to waste any coal because let's say that if you just provide half of the oxygen required by the co-combustion, then what happened to those unburned coal, right? It's not very economical, right? And also, let's say that if you reduce temperature, then you're not going to be able to heat enough of the water vapor, convert them into the steam and then drive the turbines, right? And of course, we want to increase the residence time a little bit longer because you want to have enough of the contact time for the flue gas and the water, right? So these are quite counterintuitive. So how do we achieve the NOx control while we could still burn these coal completely, all right? So there are indeed some ways to do that, and we're going to introduce that later on. But basically, these are the direct thought that we could get to reduce the NOx formation. But actually, if you expand them, there could be more detailed steps. So, for example, there are the same number of strategies, right? The strategies are exactly the same as what we discussed. Reduce the temperature, right? It specifically mentioned the peak temperature. So the peak temperature is very important because if you go back to the reaction rate, right? If you remember the K+1, the rate constant, right? That is a function of basically temperature, some value here. So what that means is that this reaction rate here is going to be an exponential increase as a function of temperature, right? So what that means is if you can reduce this peak temperature to a little bit lower, right, then you could have a lower NOx formation. Okay, so actually it's the peak temperature that determines NOx formation, not the temperatures that are in lower regions, right? So it's the highest temperature that determines the NOx formation. So in order to reduce the peak temperature, what we could do is we could use a fuel-rich primary flame zone. So what that means is that we can actually provide less oxygen, so more fuel, burn it at the fuel-rich condition, right? So basically reduce the oxygen. If you reduce the oxygen concentration, you're going to have a lower temperature, right? And you could increase the flame cooling, right, by just adding more dilution air, right? And also, as I mentioned in the third one, so you could decrease adiabatic flame temperature by dilution. So the second one is to reduce the residence time. Okay, as we mentioned, we need to get the temperature reduced, get the time reduced, right? So reduce the residence time in the hottest part of the flame zone. And we can do that by changing the shape of the flame zone. So for example, if we think about the flame, they generally look like this, right? So it's like a vertical flame, but we could actually design it specifically so that the flame is coming out of a nozzle, right? So in this way, if you consider the air residence time, so if the flame is vertical, then you're going to have a higher height and also a higher residence time. But if the flame is horizontal, then if you consider the time, right, you're going to have a shorter height and also a shorter residence time. And you could also use the steps listed in strategy 1, right? For example, add more oxygen into the reaction here to reduce the temperature and also reduce the residence time. Okay. So the third one is to reduce the oxygen content. So we said you can also get oxygen reduced, right? So what we can do is we can decrease the overall excess air rates. So if you remember, we said that in order to completely burn the coal, what people typically do is that they can add 50% or 100% more of the air into the combustor, okay? So instead, we do not provide that much of excess air. We could use, let's say, 50% or either use, or even use 25% more air into the combustor so that we don't generate that much of the NOx, right? So we could also control the mixing of the fuel and the air. So we're going to give an example later on, or use the fuel-rich primary flame zone. So this is exactly the same thing as the first one here. Okay. So these are the combustion modification methods. So now, if we just recall the method that we use for the SOx control, okay? So if I just list the SOx and NOx. So in SOx, we said that there is fuel desulfurization. Or let me just move this thing down here. Okay, we could also have the flue gas desulfurization. Okay, so if you consider the fuel desulfurization, flue gas desulfurization, so basically one of them is pre-combustion. And the other is post-combustion. What this NOx formation or the NOx control method, it shows it during combustion, let's say an in-combustion method. Okay, so basically for the NOx control, we're using basically changing the combustion conditions, either by controlling the temperature or by controlling the oxygen. We're achieving this in combustion method. This is combustion modification. So for the NOx control, we don't necessarily have the fuel or the pre-treatment method. Okay, so it's very difficult to conduct those reactions. But we could also do the post-combustion method for the NOx. So that is where the catalytic converters or the catalytic reactions came into the picture. Okay, so I would say that for the NOx control, we could have in combustion and post-combustion. But for the SOx control, we're mainly using the pre-combustion and post-combustion method, and we don't have that in-combustion method. Okay, so these are the strategies that we could use to control the NOx formation, right? So how do we really realize it? So there are multiple engineering ways to realize these in-combustion modification, right? For example, you could use the low excess air firing, the LEA. That basically just means that you can only provide 25 or 10% more air into the combustor so that you don't have that amount of oxygen to form the NOx, right? So you can also use the off-stoichiometric combustion or the OSC, but this is often called the overfire error, okay? So the OFA. So what the overfire error means is that, let's say we have the flame that is basically a horizontal flame, right? So when you burn this flame here, what you do is that you generate, first, you have to provide those co-particles, right? You have the co, and you also need to provide some oxygen. So we conduct this combustion here under the equivalence ratio larger than 1, okay? Basically under the fuel-rich condition. So to save the energy of the unburned coal, what we're going to do is we're going to introduce another nozzle, okay, to just provide the air. So that's why it's called the overfire air, okay? So the air here is over the fire so that the extra air can burn all of those unburned coal or the hydrocarbon in the coal. Right. So in this way, you can still extract all the energy that's coming out of the coal, but at the same time, you reduce the temperature in this region. You also reduce the oxygen in this flame region so that you can reduce the NOx formation. Okay. So there are also other strategies. You could have the flue gas recirculation. So what this means is that you just recirculate the already burned flue gas right? So in this way, you can reduce the overall temperature in the combustor. You can have the gas reburning. You can basically bring the flue gas into the combustor, right, to run it again. You can reduce the air preheater or reduce the firing rate. This is the same to reduce the temperature, right? Or you could even inject water into the combustor. So this is more like firefighting, right? You just introduce water in there to absorb those extra heat, and then to reduce the temperature. Okay, so how do they really look like, right? So if you think about the co-combustion method, it is never the same as the charcoal combustion, right? It's never the situation where we just set up the grill and then burn those coal particles. So as you saw from the video that I showed the other day, right, you have to grind those coal particles into the size of baby powder. You think about the size of the baby powder, that's very, very fine, right? You have to burn the coal under that condition. All right. So if you look at the how the coal combustors typically set up, so you can look at this schematic diagram here, right? So the pulverized coal is going to be carried by the air, right? So the coal are basically in the form of the particles and introduce them into the combustor, right? And then at the same time, you could have the air that's injecting into from the side of the combustor. So basically the air here is going to get introduced at a very large speed. So if it has a very large speed, then it's going to create a low temperature, a low pressure zone. So it's going to draw these coal particles into the combustor. Okay, so in this way, you could also light up the flame, right? But typically under the coal-fired power plant operation, the combustor is already very hot, right? You have a very high temperature. So you don't have to ignite these flame here. It's going to get automatically ignited because of the high temperature, okay? So just to give you a more visual understanding of this combustion process. So this is how a combustion nozzle looks like. Okay, so you introduce a coal into an open space, right? And then you light it up. But I don't think this is a real combustor because you could see this chair here. I think this is probably conducted in some lab space. But it will definitely fail the safety regulation, right? You don't want to put anything combustible near a flame here. Okay, so this is how the flame or the combustor typically looks like in the coal-fired power plant. So here I also have two short videos to show you about the co-combustion process. So let's see. Okay, so this is one of them. This is for a coal-fired power plant that has 500 megawatt. So this is just the blower just warming up. So you can see some of them are actually turned off during this operation process. This is how the flame looks like. You can see that we're burning it through a horizontal flame. You see that some of the burners not even used. Right, this is a nozzle. The coal is being introduced from the center, and then there's air coming out from the side. There are more nozzles in operation. And you can see that there are actually a lot of nozzles in this cluster. Right. Okay, so this is one of them. There is also another one. This is an 800 megawatt co-combustor. This is, I would say the flame looks brighter, right? So if it looks brighter, it means that the temperature is higher in this scenario. Okay. So let's get back. All right. So as I said, there could be many ways to control the NOx formation, right? And one of the most important control method is actually the overfire error. So I just draw a very simple schematic diagram earlier, but what it really looks like is that we're just introducing more air into the combustor. Okay, so this is overfire air, and it's being introduced from, let's say, from these nozzles here. Okay, and below these air is going to be the co-combustion nozzles, right? And we also combust these coal under a fuel-rich condition, right? So as I said, shown here, right? So the fuel-rich condition is going to reduce the oxygen, right? Reduce the temperature, right? And also, since we burn them in through this horizontal flame here, so the residence time is also reduced. So in this way, we actually achieve all of the three requirements to reduce the NOx formation, right? So basically, what it really looks like in a co-combustor is that, let's say this is our nozzle, right? You're going to introduce the coal in there, and then this is a fan, right? So the fan here is going to introduce those overfire air that's right above these coal nozzles, right? To basically consume the rest of the hydrocarbons. So the overfire air will just react with the remaining coal so that we don't waste any energy coming out of the coal. Okay, so this is how the entire boiler looks like. So right now we have just talked about the combustion region, right? So after the coal is being burned, these high temperature flue gas is going to go through these water pipes to generate steam, right? And then you're also going to send the air through a preheater. So this preheater, what it does is going to extract the extra energy. Okay, so if you see that the temperature after the temperature of the flue gas after these water pipes are still pretty high, 600 Fahrenheit. If we directly emit them through the stack, then it's still a waste of the energy. So what we can do is we could actually extract the remaining heat by introducing them through a heat exchanger. So what it does is basically the hot flue gas can go through those small channels or the small tubes. But at the same time, the air that's planned to go into this combustor here, we introduce them around those pipes, okay, around those channels. So you can have a heat exchange and warm up these fresh air, warm them up into the temperature of, let's say, close to 100 Celsius, right? So in this way, you can extract the heat and then introduce them into the combustor so that you can further increase the reaction rate and also the temperature of the flue gas. So this is another way to save the energy out of the combustion. Okay. So we said that basically these NOx control methods are in combustion methods, right? This is the combustion modification. And we said that for the NOx control, there's also post-combustion method. And this is actually the flue gas treatment techniques, okay? So in terms of the flue gas treatment for the NOx, there are selective catalytic reduction, the SCR, right? And there can also be selective non-catalytic, so something that do not need any catalyst to go through this reduction here. This is SNR. You could also adsorb these NOx or use some wet adsorption methods. Okay, so basically for the SCR process here, what it really means is that if you consider the composition of the NOx. Okay. So NOx is basically a nitrogen attached with several oxygen. And then are there ways to basically convert these into nitrogen? Okay. So one thing we can do is by adding ammonia into the reaction here. Okay. So if you have ammonia, then what happens is the hydrogen is going to combine with the oxygen and then form water. Okay. Of course, this reaction is very difficult to occur. It has to happen at certain temperature region. For example, the temperature here is typically in the range of 300 to 400 Celsius, which is 600 to 800 Fahrenheit. Okay, so there has to be a temperature window. And also, to let this reaction to occur, you have to provide some catalyst. So typically, people would use titanium dioxide or vanadium oxides. Okay, so to use those as the sites for this reaction to take place. Okay, so in terms of the reaction that's really happening, we can write them out. So it's 4 nitrogen monoxide reacting with 4 ammonia and an oxygen going into 4 nitrogen and 6 water. Or if you're dealing with nitrogen dioxide, okay. So if you're dealing with nitrogen monoxide or nitrogen dioxide, you have to use different ratios of these nitrogen oxides or ammonia. So as we said, for this reaction here, you have to get a correct temperature region. So the reason is that if temperature is too low, then this reaction is not going to take place at all. Okay, so basically you introduce ammonia into the flue gas, and ammonia is not going to react with NOx. Then you're going to have the double pollutants, right? So ammonia is also an air pollutant, and you don't want to emit it into the atmosphere. But if the temperature is too high, then what happens is this reaction here is not the priority anymore. So the priority, or the more important reaction, is just the ammonia getting oxidized. Okay, if it gets oxidized, you're going to form NOx and water. Okay, so basically, if the temperature is too high, let's say about 400 Celsius, then you're going to form more NOx instead of reducing the NOx concentration. So that's why the temperature is very important in this reaction here, and people have to design their co-combustor really well to control these species. Okay, so finally, there's a short video again. I think this is one that we have already gone through in our previous class when we talk about the sulfur oxide. Maybe we can just quickly go over it again. So that's the Alabama coal-fired power plant. Okay. All right, so this is the SCR. SCR is the selective catalytic reduction, right? So that's for that's basically for controlling the NOx formation.
While the heavier particles of ash fall to the bottom of the boiler, the hot flue gas containing finer particles of fly ash naturally flows up to the top of the boiler and around, down, and out through the backpass section. The last section of the boiler is the economizer. Because of the shape and the flue gas flow path, some of the fly ash falls out here into hoppers. This economizer ash is pulled by vacuum, mixed and sluiced with water to the ash booster station where it is moved to on-site storage. Flue gas, a byproduct of combustion, exits the boiler and enters the selective catalytic reducer, or SCR. While entering the SCR, ammonia is injected into the flue gas stream, where it reacts with several catalyst layers to reduce the nitrogen oxide compounds. The flue gas then passes across the air heater where over 400 degrees of temperature are transferred from the exiting flue gas to preheat the primary and secondary air entering the plant.
Yes,
Next,
you see that
the flue gas
basically
passes through the
from the
precipitator
SCR,
to preheat the
these
primary
are the
across with several CR.
nozzles that
While
introduce these ammonia into the system, right? And then on the other side here, we have the catalyst to let the reaction to occur. Okay, so that's it for the contents of this class. So next class, we're going to talk about the carbon dioxide control. All right, thank you.